All right, so we are now going to discuss about power series. All right. So you should have noticed the following. The name of the course is Calculus 2. So in calculus, what we really do usually is we try to study small changes in the function, right? So why did we go into the discrete business, right? We went to study summation 1 by n square, for example, right? So there's no small change really. So we were trying to prepare for what is called as power series. So the idea behind this is the following. Some of the functions, say for example, sine x, you'll see soon that sine x can be written as 1 to the power n, x to the power 2n plus 1 upon 2n plus 1 factor. So now you can see that this function, which is a continuous function, actually it's a differentiable function, can be written in terms of a power series like this. Other motivation is, so this is how your calculator computes your sine x values, right? Another idea is that we know that we cannot have an elementary antiderivative of this. So if somehow we can write a power series of this, you will see that the power series of e to the x is going to be n equals to 0 to infinity x to the power 2n upon n factorial. We'll see that later when we are doing Taylor series and stuff. And then you can integrate each term by term and find the integral, at least an approximation for the integral, at least a series expansion for the integration, right? So it helps you basically to perform the calculus, right? So what is a power series, first of all? So power series is a generalization of a polynomial. So what is a polynomial? So polynomial of degree n is a function of form c0 plus c1x plus c2x squared all the way until cnx to the n. These c0, c1, c2, c3, cn are the coefficients of this polynomial. And if cn is not 0, we say the degree of p of x is n. So power series is a generalization of this idea in the sense that you have c0 plus c1x plus c2x squared, so on, but you never stop. You keep on going forever. So this can be written in the following form. This can be written as summation n equals to 0 to infinity c n x to the power n. Again, these c0, c1, c2, c3 are called coefficient of power series. And in some sense, they are the defining feature, right? What is different about two power series? If I tell you, oh, take another power series, this is how it will look like. So what is really different in both of them is not x to the power n part, but the coefficient part. So the coefficient part is the important part in some sense. All right. Now, sometimes you base, instead of having x, x square, x cube, and so on, you basically have c0 plus c1 x minus a plus c2 x minus a square, so on and so forth. This is called power series centered at a. And you can write this in short as cn x minus a. You can write this as summation n equals to 0 to infinity cn x minus a to the power n. So such a power series is called power series centered at a. All right. We'll see later why centering a power series around a point is more sensible other than just looking at these power series. It gives you a better estimate of the things. Okay, so we'll come to that. Now let's answer the following question. So suppose you're given this power series. Yeah, then the question is, for what values of x does this power series converges? Yeah, how do we find it? So what are the things we have in our hand? We have, so here the question is different. Here you're not saying, oh, does this power series converges or not? Yeah, we are answering the question, for what value of x does this power series converge? See, note the following. This power series will converge at least for one value for sure, and that is the center, which is 2. Because if x equals to 2, you will get what? Summation n equals to 1 to infinity minus 1 to the power n, 2 minus 2 to the power n upon n times 4 to the power n. And this will be 0, right? So it's basically adding bunch of zeros. So you get 0. So at x equals to 2, this power series converges, right? So the convergence of the power series is guaranteed at the center. So our question is, for what values of x does this power series converge? Okay. So for that, um, we'll basically employ the following. So how do we basically see for what values of x does it converge? Okay. So let's keep this as a motivational question, and we'll try to come to it. Similarly, let's look at this function, which is called Bessel's function of order 1. It's an important function in differential equations. Uh, so what is the domain of this function J1? Yeah. So if you're asked about the domain, essentially you're saying for what values of x does the output make sense? So essentially you're asking when is for what values of x does this series, does this power series converge? So we need to answer these questions, all right? So this is what is the goal of this lecture, that we want to understand for what values of x does the given power series converge, okay? So let's move ahead along that line. So, so let's look at the following. So suppose you're given a power series summation n equals to 1 to infinity, say Cn x minus a to the power n. Now let's apply a ratio test on this. So if you apply a ratio test on this, what do you get? You will get Cn plus 1. So limit as n goes to infinity. So what is the n plus 1 term? Is going to be x minus a to the power n plus 1 divided by Cn x minus a to the power n, and you're taking absolute value of this. Then you get limit as n goes to infinity of, so this will cancel out, you'll have x minus a times Cn plus 1 upon Cn with the absolute value. And let this be, so if this is less than 1, then convergence is guaranteed. If this is greater than 1, then we have divergence. And if this is equal to 1, the test is inconclusive. Do you agree? Yeah. So let's choose to call this as, let's move this. So let's see, let's hope that this is not 0 and bring it on the other side. So what do I get? So if I bring it on the other side, x minus a is less than Cn upon Cn plus 1. And let's call this as R. Yeah. So in that case, what will we get? Uh, if we have x minus a is less than R, which is same as case less than 1, then we have the series converges. And if this is greater than R, then the series what? Diverges. And if x minus a absolute value is equal to R, then the test fails. And we need to do something else to check that. Yeah. So this is basically this statement is summarized here. So for power series, there are only three possibilities. So first of all, it will converge only at the center, one, or it can converge for all values of real numbers, okay? Or basically it converge, there's a positive number r such that x minus a less than r would lead to convergence and x minus a greater than r will lead to divergence. So such r is called radius of convergence. And so let's see the following. So if you have x minus a less than r implying convergence, this would mean minus r less than x minus a less than r. This means x is greater than minus r plus a less than r plus a. So you see, r in this interval is guaranteed to be convergent. Yeah. So we get an interval out of it where the function, sorry, where the power series is convergent for sure. So if I draw this, here's how it's going to look like. So you have center of the series. Okay. Then you have x in between a minus r, which is same as r minus r plus a, and a plus r, the series is convergent for sure. Outside this, the series is divergent for sure. And at the endpoints of this interval, there is a convergence. Sometime it converges, sometime it diverges. So for that, we have to employ a special test and check at these points separately. Okay, so this is how we go about convergence of power series. So let's look at an example first. So let's go back to our original example here. So for what values of this it converges? So we know for sure for two it converges, but for what are the exact values for which it converges? So now we'll use the ratio test to decide that. So what is limit as n goes to infinity of an plus 1 over an? This is limit as n goes to infinity of minus 1 plus 1 x minus 2 to the power n plus 1 times n times 4n plus, sorry, n plus 1 times 4n plus 1. Let me write in a different color so that it's clear. And I have an. So I'll use a different color for this, an. And then I have an is basically dividing by an is multiplying by the reciprocal. So we have minus 1 to the power n, x minus 2 to the power n, n times 4n. And then we are looking at the absolute value of this, right? So now let's see. So minus 1, because of the absolute value sign, minus 1 to the power will disappear. You have x minus 2 to the power n, and you have x minus 2 to the power n plus 1. So what will survive? X minus 2. An absolute value sign, limit as n goes to infinity. Now what will survive in the bottom? So this 4n plus 1 and this 4n, so they will cancel. You'll have basically 4. Then there is n and n plus 1, so n upon n plus 1. And if you look at this limit, this is going to be x minus 2 by 4 with an absolute value sign. And this is less than 1. So this implies for x minus 2 less than 4, your power series converges for sure. Right? And if you rewrite this thing here, again, for x minus 2 by 4 bigger than 1, it diverges. That means what? For x minus 2 bigger than 4, it diverges. Yeah. So here, the radius of convergence is going to be what? Convergence is 4. Okay. Now, what about the interval of convergence? So for interval of convergence, note that following. So x minus 2 less than 4 implies minus 4 less than x minus 2 less than 4. Now this implies minus 4 plus 2 less than x less than 4 plus 2. So this means minus 2 less than x less than 6. So inside here, the convergence is guaranteed. And outside, we have to just check at the endpoints now to see what happens, right? So at endpoints, so we check separately for the endpoints. So let's take x equals to, what are the endpoints? X equals to -2, and you substitute that in your original power series. So we get what? Summation n equals to 1 to infinity minus 1 to the power n minus 2 to the power n divided by n times 4 to the power n. And here we get summation n equals to 1 to infinity minus 1 to the power n times minus 4 to the power n divided by n times 4 to the power n. If you simplify this, you can combine these minus 1 to the power n minus 4 to the power n together. You'll get summation n equals to 1 to infinity minus 1 to the power. So you'll get minus 1 times minus 4, which is 4 to the power n divided by n times 4 to the power n, which is summation n equals to 1 to infinity 1 by n, which is a p series with p equals to 1, so diverges. Now, similarly, at other endpoint, x equals to 6, what do we get? How will our power series look like? Summation n equals to 1 to infinity minus 1 to the power n times 6 minus 2, which is 4 to the power n, divided by n times 4 to the power n, which is summation n equals to 1 to infinity minus 1 to the power n divided by n, and this converges. Why? Because of alternating series test, right? So therefore, what is the interval of convergence? Let me write it with a different pen here. Interval of convergence is what? Is -2 to 6. -2 we checked out is excluded, and 6 was included. So this is how you find out the uh, the radius and the interval of convergence. All right, so now let's discuss the interval of convergence for the following series. So generally you'll be asked, or you should be asked, what is the find the radius and interval of convergence. All right, because without finding the radius, finding interval of convergence is going to be much more challenging. So let's proceed with this. So first one, A. So in this case, I can apply the root test as well. All right. So let's see. So So for power series, you should apply either the ratio test or the root test to find out the radius of convergence. Okay. So let me apply, just to keep a problem different, let me apply the root test here. So limit as n goes to infinity of nth root of an. So this is going to be limit as n goes to infinity of nth root of n to the power n xn. That is limit as n goes to infinity of nx, right? And that is what? Infinity, right? So this is never less than 1 if x is not 0, right? So it doesn't converges for anything except for the center, which is 0. So in this case, radius of convergence is 0. Why? Because see, the idea behind radius of convergence is, say, what is the center of this? Center of this series is, so if you write it like x minus a to the power n, a is the center. So in this case, it's like x minus 0 to the power n. So you have 0. How much you go on each side and still have convergence? That is what the radius of convergence is, right? Let's see. Let's reevaluate what is done here in the previous problem, right? So first problem. So if you look at this problem here, your radius of convergence is 4. In some sense, you're starting with 2, the center, and how much you're going on each side. So on this side, you went 4, and you go 4, you get 6 to 6. On this side, you go to 4, you go to minus 2. So you see, it's really like a one-dimensional version of circle, right? So you go 4 on this side, 4 on the other side, and that is what gives you the radius of convergence, all right? And then you check for the endpoint separately, of course. So same thing here as well. It doesn't converges for anything except 0, the center. So the radius of convergence is 0, and in that case, the interval of convergence is also 0. Not because of this, but only the center is there in the interval of convergence. Okay. So this was a straightforward problem. Let's move to the next part. B. Now we have summation n equals to 1 to infinity x to the power n over n times 3 to the power n. So first thing is to find the radius of convergence. For that, you'll use the ratio test. So limit as n goes to infinity of an plus 1 divided by an, which is going to be limit as n goes to infinity. What is my an? Is going to be x plus 1 n plus 1 times 3 to the power n plus 1. And divided by an is, so what is my an? An is the same thing. Since I'm dividing by an, I'm multiplying by the reciprocal. N 3 to the power n divided by x to the n. Okay. So now let's cancel off the terms. So this x to the n plus 1 and x to the n, so they will cancel. You'll get limit as n goes to infinity of absolute value of x. What do you get on top? This 3 to the n and 3 to the n plus 1. Only 3 will survive in the denominator. On top you have n, on bottom you have n plus 1. I mean, I'm writing it outside the absolute value sign because this is positive, right? And as n goes to infinity, this is 1. So you have x minus 3. Yeah. So if this is less than 1, then what happens? The power series converges. So converges. that is same as saying absolute value of x is less than 3. So in that case, you already get the radius of convergence. I'm going to write it in short, r dot o dot c, which is radius of convergence. So now from now onwards, I'll use this short notation, is basically 3. Okay. Now the next step is to find the interval of convergence. So for interval of convergence, what we'll do is we will basically take this and expand. We'll get absolute value of x less than 3 implies minus 3 less than x less than 3. Okay. So here the convergence inside is guaranteed. And now the next step is to check at end points. So what are the two endpoints we got? X equals to, first endpoint is x equals to minus 3. I'll put it back in the equation in the power series, sorry, n equals to 1 to infinity minus 3 to the power n times 3 to the power n. I can split that top up, the numerator, into minus 1 to the power n, 3 to the power n divided by n times 3 to the power n. These guys cancel off, and you have summation n equals to 1 to infinity minus 1 to the power n over n. And you have already seen that this converges using what? Alternating series test. Okay, now what about the other endpoint? X equals to 3 will have summation n equals to 1 to infinity 3 to the power n, right? Instead of x, I'm going to put 3 to the power n, instead of x, I'm going to put 3, so it becomes 3 to the power n. So this is going to be summation n equals to 1 to infinity 1 by n, and that, diverges y p series with p equals to 1. All right. So p series with p equals to 1. Therefore, the interval of convergence is going to be minus 3 to 3. Minus 3 is included, 3 is excluded. Okay, so this is how you go about the whole game. All right, so let's look at the following problem. Again, our problem is to find radius of convergence and interval of convergence. All right. So same story, we have to start with ratio test to find out the radius of convergence. So limit as n goes to infinity of an plus 1 divided by an. This is going to be limit as n goes to infinity an, which is going to be minus 2 to the power n plus 1 times x to the power n plus 1 divided by, now instead of 2n, I have n plus 1, right? So I'll write it down properly. So it's going to be 2n the whole. Instead of n, I have n plus 1. So that will be in the bracket factorial. Okay. So we have an, which is going to be minus 2 to the power n, x to the power n, and what do I have on top? 2n factorial. So now before I do the cancellation, I need to expand this guy, right? So let's expand this a little bit. So we have limit as n goes to infinity. So I have minus 2 to the power n plus 1 and 2 to the power n. That will cancel out. So you'll be left with 2 on the top. X to the n plus 1, x is left out. Now we have to deal with the factorial business. So note that this is same as 2n plus 2 factorial, right? Do you agree? So in that case, we can write this as, so what is 2n plus 2 factorial? We have to bring it down to 2n. So 2n plus 2 factorial is 2n plus 2 times 2n plus 1 times 2n factorial. all right? And on top you have 2n factorial, and the rest we already took care of. So this guy will cancel off with this guy. You're left with limit as n goes to infinity of 2x upon 2n plus 2 times 2n plus 1. This. Now as n goes to infinity, see, think about x, whatever number x is fixed at once. So as n goes to infinity, this whole thing goes to 0. And no matter what, that is going to be less than 1. So independent of x, it's always less than 1. So this means what? It converges for all x, right? So now let's see what is the radius of convergence. So interval of convergence is clear here. Here in this case, we get interval of convergence first, which is minus infinity to infinity. So we are writing real numbers as set of real numbers as an interval. Now what about radius of convergence? Think about it. So we have 0 here. And how much are we going on each side? There's no stopping to it, right? So you're basically essentially going, I mean, infinity is not a number to go up to. So in this case, the radius of convergence is going to be what? You keep on going forever. So the radius of convergence is infinity. So this is how this problem goes. Okay. You recording? Okay. So now the question is, can we write down this function as a power series? Okay. So later on we'll see some better techniques, but do you recall? So what is summation? So if I take 1 plus r square plus r cube, so on and so forth. And if I write it in short, this can be written as summation n equals to 0 to infinity r to the power n. So this is an example of a geometric series, right? So you remember that here so a is 1 and r is r, well, of course. And this converges to a upon 1 minus r, which is same as 1 upon 1 minus x, if absolute value of x is, or in this case, it converges to 1 upon r when absolute value of r is less than 1. Yeah, so here r was a fixed quantity, but if I replace r by x to represent a variable, then I have the following. So summation, let me write it other way around rather. I have 1 upon 1 minus x is equal to summation n equals to 0 to infinity x to the power n, right? So this is a power series of the function 1 upon 1 minus x. However, this is only valid when absolute value of x is less than 1. Otherwise, it's invalid, right? Because otherwise, this thing doesn't converges. So we have 1 upon 1 minus x as this thing. Okay. So this is your function f of x. And this is a power series representation of your function. So power series representation. Note that this power series representation is only valid for absolute value of x less than 1. Otherwise, this function is not, they are not equal, right? So let's move ahead. Let I be the interval of convergence for the power series, summations n equals to 0 to infinity. Then for each x in I, f of x, when it is written like this, n equals to 0 to infinity, cn x to the power n, then we call this power series as a power series representation of your function. Okay. So now the first step is to find power series representation of certain functions. Okay. So first, let's look at the power series representation of this function here. So now in this case, we have to build everything out of 1 upon 1 minus x. So we have 1 upon 1 minus x is going to be summation summation n equals to 0 to infinity x to the power n, right? So before we go and do problem A, let's see what is 1 upon 1 plus x going to be. So 1 upon 1 plus x is going to be summation. Well, before I write that summation, I will convert it into the previous form. So it's going to be 1 upon minus of minus x, right? Mute all. And then now in this formula here, instead of having x, you have minus x. So this is going to be summation n equals to 0 to infinity minus x to the power n. And then you have to simplify it a bit. So it's going to be n equals to 0 to infinity minus 1 to the power n, x to the power n. And note that this is all valid when absolute value of x is less than 1. Otherwise, this is not valid. So this is so 1 over x can be represented as this power series here. Okay. So this is the power series representation of this function. So now out of this 1 and 2, we'll construct the other ones. Okay. So first, let's look at A. So the problem is asking you to find power series representation. That means you have to expand this in terms of power series. So let's see. So we have f of x equals to 1 upon 1 plus 4x squared. So if you think about this, it's 1 upon 1 plus box, right? So for which we have formula over here. So this is going to be, and the formula expands to here. So this is going to be summation equal to summation n equals to 0 to infinity minus 1 to the power n. But instead of x, you will have 4x squared to the power n. Yeah. Let me digress a bit more. So the upshot of this formula, the first one here is 1 upon 1 minus box is summation n equals to 0 to infinity box to the power n. Yeah. And of course, this is only valid when whatever is inside the box, if you take absolute value of that, has to be less than 1. Similarly, for the other one, you have 1 plus box is going to be summation n equals to 0 to infinity minus 1 to the power n box to the power n, right? Again, and this is only valid when box, absolute value of box is less than 1. So whatever is inside that box. Make sense? Okay, so here let's write it down. So we have, this is going to be summation n equals to 0 to infinity minus 1 to the power n 4 to the power n, x to the power 2, the whole power n is going to be x to the power 2n. So this is your power series representation of the function. But this is not enough. You have to also specify the interval of convergence. So for that, we already have that 4x squared has to be less than 1 because whatever is inside the box has to be less than 1. This implies 2x the whole square is less than 1 in the absolute value sign. This would imply that 2x the whole square is less than 1. This implies 2x is less than 1, absolute value of this. Now I can break this into two parts. So we have absolute value of 2, which is 2, is less than 1, or this implies absolute value of x is less than 1 by 2. So this formula, that this being equal to this, is only valid for what? Only valid for, let me rewrite this again. So I have 1 upon 1 plus 4x squared. This is only valid. So this is equal to summation n equals to 0 to infinity minus 1 to the power n, 4 to the power n, x to the power 2n. And this formula is only valid on on absolute value of x less than 1 by 2. Or if you want to write the same thing in the interval notation, or x belonging to minus 1 by 2 to 1 by 2, right? Because you can convert this into an interval notation. So these formulas are equivalent only in this interval. Okay, make sense? All right. So let's move to the next part. Problem B. So problem B, we have g of x equal to this guy. So first we'll again do the construction out of the out of 1 upon, so we have 1 upon 1 minus x. We'll do the construction out of this. So first let's write that in this form. So note that this can be written as x upon, take 9 common, what is left in the bracket? 1 minus x square by 9. This is going to be x upon 9 outside multiplied by 1 upon 1 minus x square by 9. So this is your box, and then you can write it as x by 9 outside summation n equals to 0 to infinity x squared by 9 to the power n. And then you can simplify this to be summation n going from 0 to infinity x to the power 2n divided by 9 to the power n. And on outside you have this x by 9, which will multiply inside, and you'll get summation n equals to 0 to infinity x becomes x times x to the power 2n, the power goes up by 1, and similarly for 9 the power goes up by 1. Okay, so the power series of this guy is equal to this. And where is it valid? It's valid when absolute value of x squared minus 9 is less than 1, which implies x squared, absolute value of x squared is less than 9, which implies x is less than, absolute value of x is less than 3. So this formula is valid on absolute value of x less than 3, or which means x belongs to minus 3 to 3. Okay, this is a side computation. So this is how you write down the power series of this guy. So so suppose your function f of x is written by a power series of the following form. Yeah, and this is again valid on the radius of convergence r greater than 0. Then clearly, even though, so if this is also valid at the endpoint, so suppose you have one endpoint is included, the other one is not, still when we are talking about the derivatives, we will not include the endpoints. Okay, so the idea is, suppose your f of x is differentiable on, so suppose your f of x is given by the power series summation n equals to 0 to infinity cn x minus a to the power n with radius of convergence equals to r, then your function is differentiable on a minus r to a plus r. And what is the derivative? The derivative is, let's see. So what is the derivative of this function? So we'll basically have derivative of this is same as n going from 0 to infinity cn d by dx of x minus a to the power n. So taking derivative on both sides and moving the derivative inside, this is going to be summation n equals to 0 to infinity c n times x minus a to the power n minus 1. But hold on, before we write it like this, you see when n is 0, this will be minus 1, and that representation is not allowed in the power series, right? But notice the following, when n is 0, this term is going to be 0 as well. So you can write this, the proper way to write this is n equals to 1 to infinity, because the 0 term is going to be 0 as well, again, right? So we have cn n times x minus a to the power n minus 1. So you should start with n equals to 1. right? Even otherwise, you can look at from the other perspective as well. So suppose your f of x is going to be c0 plus c1 a x minus a, c2 x minus a square, and so on and so forth. When you take the derivative of this f prime x, the first term becomes what? 0, right? So you have c1 and so on. So that's why when you write it down, it starts with what? It starts with n equals to 1 when you take the derivative. All right. Now, similar thing can be done about integration as well. So let me write down the integration here. So your f of x is, again, summation n equals to 0 to infinity cn x minus a to the power n. So integration of f of x dx is going to be summation n equals to 0 to infinity, integrating on both sides and moving the integral inside the summation. This can be done when your x is within the interval of convergence. So what do we have? We have summation n equals to 0 to infinity cn. What is integration of x minus a to the power n? Is x minus a to the power n plus 1 upon n plus 1 plus some constant ci. Well, let's use a different constant, ki, and you can collect all those constants together in the end to call it a big C. We have summation n equals to 0 to infinity cn x minus a to the power n plus 1 divided by n plus 1. So this is the integration of the power series. All right. So, so let's move ahead. Now note that you have to basically make the connection with 1 upon 1 minus x or 1 upon 1 plus x in this cases. So let's look at the first one. So can you notice the following? What is derivative of 1 upon 1 minus x? That is going to be what? So this is going to be minus 1 upon x minus 1 the whole square multiplied by derivative of inside, which is minus 1. So you get 1 upon 1 minus x squared. So now you can see we already know the power series for this guy here, right? And we'll use that to basically get the power series for the derivative. So let's just do that. So we have, let me do the problem A. So f of x equals to 1 upon 1 minus x, which is given the power series representation is n equals to 0 to infinity x to the power n. So therefore, and this is valid when absolute value of x is less than 1. So therefore, differentiating on both sides, with respect to x, we get derivative of this is going to be d by dx of 1 upon 1 minus x is 1 upon 1 minus x square. And on the other side, we get what? Summation n equals to, instead of starting with 0, you'll start with 1. Going from this to infinity, derivative of x to the n is n, x to the power n minus 1. And again, this is valid for absolute value of x less than 1. So you got your power series representation here, right? Oops. So your power series, this is valid for absolute value of x less than 1. And okay, so here is your power series representation. Okay, seems like my computer is gotten hot now. So okay, it's misbehaving. Anyway, so this is the power series representation right here. Yeah. So when you're giving the power series representation, it's not just the first part is important, but also in what range or what interval
is this equation valid? Okay. So now let's look at the next one now. So next one is B. So we have, so now we want to see the connection. So notice the following. So ln of 1 plus x, how do we get it out of either 1 plus x or 1 minus x? So notice that this is going to be integration of 1 upon 1 plus x dx. If you integrate this, you get ln x plus a constant c, right? So let's do that. So we already know the c is expansion for 1 upon, we get c is expansion for 1 upon 1 plus x, which is 1 upon 1 plus x is summation n equals to 0 to infinity minus 1 to the power n x to the power n. So integrate on both sides. So integration of 1 upon 1 plus x dx is going to be summation n equals to 0 to infinity minus 1 to the power n integral of x to the n dx. Note that this can be only done when absolute value of x is less than 1. So this is going to be summation n equals to 0 to infinity minus 1 to the power n x to the power n plus 1 divided by n plus 1 plus a big constant c here, and in this case we have ln of 1 plus x. You will say, oh, why I need a constant here too? Well, you can take that a constant, this constant, and combine them together, right? So it's up to you. So this is the power series expansion, but we need to know what the c is, right? So for that, let x be 0. So you know ln of 1 is going to be summation n equals to 0 to infinity minus 1 to the power n, 0 to the power n plus 1 upon n plus 1 plus c, which will give me ln 1 is also 0. So this is 0, right? So we get c equals to 0. So this leads us to the following, that ln of 1 plus x is the power series summation n equals to 0 to infinity minus 1 to the power n x to the power n plus 1 divided by n plus 1. So this is how you write down the power series of this guy. All right. So next problem is about arc tan x, or tan inverse of x. So notice the following. What is arc tan x? Arc tan x is nothing but integral of 1 upon 1 by x squared dx. Yeah, plus a constant, right? So now first we need to write down the power series for 1 upon 1 plus x squared. Now recall we have 1 upon 1 plus box is summation n equals to 0 to infinity minus 1 to the power n box to the power n. So we can basically do this. So we have summation n equals to 0 to infinity minus 1 to the power n. Instead of box, we have x squared. So x to the power 2n. Now integrate on both sides. So we get integral of 1 upon 1 plus x squared dx is going to be summation n equals to 0 to infinity minus 1 to the power n integral of x to the power 2n dx. So what do we get out of that? So we have summation n equals to 0 to infinity minus 1 to the power n x to the power 2n plus 1 divided by 2n plus 1 plus a c here. And here on this side, we have tan inverse of x, or arc tan x. Now we need to find out what this c is. So again, let's put x as some value, which we already know. So we already know that x equals to tan inverse of 0 is 0. So let's take x equals to 0. We'll get 0 equals to, everything is 0 plus, so 0 plus c, therefore c equals to 0. So what do we get? Therefore tan inverse of x is going to be summation n equals to 0 to infinity minus 1 to the power n x to the power 2n divided by 2n plus 1. And this is valid when absolute value of x squared is less than 1. That is same as saying absolute value of x is less than 1. So this is your tan inverse. All right.